Now today's topic is electromagnetic waveguide S1B. Uh, it is about the transmagnetic mode, as we did in the last topic, which was transelectric mode, in which the Ez was 0 but Hz was not equal to 0. In transmagnetic mode we have Hz is equal to 0 and Ez is not equal to 0. Already we have defined that in transmagnetic the transmagnetic component, or the magnetic component, is transverse to the direction of the propagation, with the no longitudinal component of the magnetic field vector. And Ez, but Ez has a longitudinal component in that case. So in the let's now get the derivation of the equations for the related components of the E fields and the H field. In the equation 23 we have the delta 2 H by delta x square is equal to gamma square H, delta 2 H by delta x square plus gamma square H is equal to minus omega square epsilon mu H. Since H is equal to Hy and we take the Y along, now the H field is along the Y and E field will take along the X, is equal to Hy naught E square minus gamma Z. So delta 2H, if we take the second order differential and rearranging and simplifying the equation, we get delta 2 Hy naught by delta x square plus gamma square Hy naught, which is equal to minus omega square epsilon mu Hy naught. It's again the same second order differential equation. Rearranging the equation, we get the delta 2 Hy by Hy, this should be, I think I know, Y naught, yes, y delta x square plus Hy naught the L square is equal to 0. Let me correct those these two terms. Okay, I corrected those these two terms, Hy naught, now delta 2 Hy naught by delta x square plus Hy naught L square is equal to 0, where L square is gamma square plus omega square epsilon mu. So again the solution of this second order differential equation is of the kind is Hy naught is equal to now C3 sine of Lx plus C4 cosine of Lx. We mark this equation as a 40a. Hence the Hy we again replace now to this main function, which is Hy is equal to Hy naught into e raised to minus gamma Z. So this is Hy naught, we put the value back. Now applying the boundary conditions at x is equal to 0, Hy is equal to 0, so it will give us the C3 is equal to 0. At x is equal to a, Hy is equal to 0, that will give us the L is equal to m pi over a. So Hy, so we are left with the Hy is equal to C4 cosine of Lx e raised to minus gamma Z. We set this equation as 41. So since the C3 is 0, we got over there, so we are left with a C4 constant. Now from equation 20, which is given by delta Hy by delta x is equal to j omega epsilon E Z, we can get the value of Ez. Here is the equation 20. Where we were, okay, I think that was the 40. Maybe mix the thing. Okay, here's the if you take the differential of this equation with respect to x and put it over here in this equation 20, so what we get, we get the value of Ez, which is in this case is not equal to 0. So Ez is the propagation direction. So Ez is equal to m pi over j a omega epsilon times the whole bracket C3 cosine of Lx minus C4 sine of Lx e to minus gamma Z. Initially we can put back to the mean, but we can reduce it to obviously Ez, since C3 is equal to 0, so we are left with this sine Lx part. So already we have applied the boundary conditions, and Ez is given by this equation number 42. Now similarly, applying the boundary condition to equation number 41, what we get, Hy is equal to C4 cosine of m pi over A in times x e to the power minus gamma z. From the equation number 25, Ex we have got over there is given by minus gamma by L square delta Ez by delta x. If you remember, in the first topic, the electromagnetic wave guide S1, we got all these four equations Ex, Hx, Ey, Hy, but all of them were in the found to be the depending upon the differential with respect to x of the Ez and Hz, these two components. So here we are now making use of that and finding the actual solution for those particular field configuration. So simply taking the delta Ez by delta x, what we get here, you should simplify that. We get the Ex now, and putting back into this equation, Ex is gamma by j omega epsilon into C3 sine of Lx plus C4 cosine of Lx e to the power minus gamma z. Now applying the boundary conditions, again we have similarly the same at x is equal to 0, and at x is equal to a, the components we talk about, those are equal to 0. So what we have, Ex is given by gamma by j omega epsilon C4 cosine of m pi or a x e to the power minus gamma z. Since gamma is equal to minus beta z, the beta z, we can put that it should be that be over there. So that is, I think, gamma should be, that is minus j beta z. Okay, so gamma is plus j beta z. Okay, j will again multiplied over there. Gamma is equal to plus j beta z. So putting that value in this equation minus gamma, which is it is plus j beta z, just made this correction, e is minus beta j beta z. So Hy is given by this relation, which is C4 cosine of m pi over a into x, where we get the obviously C3 is equal to 0 in this case. Similarly, Ex is equal to beta by omega epsilon C4 cosine of m pi over a time x e raised to power minus j beta z again in the same term. And finally, lastly, Ez is equal to, already we have done that, m pi over j omega epsilon a C4 sine of m pi x over a times e minus j beta z. Remember, this j beta z is responsible for the propagation imaginary part. The alpha part, if this is 0, alpha part is not 0, that the wave is totally attenuated, it will not move forward. It will only move forward if that alpha is 0, that attenuation is 0, and then we have j beta z, it will move ahead. So final configuration what we have got now, this is Ex, this is Hy and Ez, but Hz is equal to 0, transmagnetic mode. So we discussed these two modes, the transelectric and transmagnetic, but there exists another mode which was supposed to be in the first place, but let me take that. This is called TEM, transelectric and magnetic mode. Since you saw that in the transelectric there was the one particular mode was 0, in transmagnetic again there was a mode was 0. Transelectric E was supposed to be the transverse to that, and Ez was equal to 0. In transmagnetic the Hz was 0. So in transelectric and magnetic, in free space, if the wave is not bounded by any two regions, then if it's wave, the electromagnetic wave is propagating inside free space, not bounded by the region, then it is having the transelectric and electric and magnetic modes. In that term, obviously, you see, if both cases, the longitudinal components will be equal to 0, longitudinal component of E and longitudinal component of H, magnetic component, will be equal to 0. In transelectric and magnetic mode, the electric and magnetic fields are transverse to the direction of propagation or the wave with no longitudinal components. Ez is equal to Hz is equal to 0. So we are left with only these Ey, Hx or Hx, Ey, these components exist, but Ez, Hz are equal to 0. Such configuration of the field, the electromagnetic fields, is called the transelectric and magnetic modes. So with this we reach to the end of the topic. See you next time, and then with a new topic and new lecture. Thank you.